Hello everyone, welcome back. Let's do some biochem. So this is the first biochem lecture we're doing, but we're actually going to start with the last lecture in biochem, because most people at this point have told me that they are nearing the end of their prep, that they are doing their UWorld and practicing and this and that, whatever it may be. And it is pertinent for me to make videos for the masses and not just for the particular, and especially not the 9th grader who thinks that they're going to take the MCAT in 20 years and then they're studying 20 years in advance. I know you, and I know you're brown. I'm 100% sure of it, right? Okay. I remember one time my mom told me, she's like, you're in 7th grade now. Got to start studying for the SAT. And I was like, no, Mom. I need to go play Call of Duty. That's what I need to do. I was playing zombies until 1 in the morning. Those are the days. Black Ops 1 zombies? Ooh. All right. I haven't played a video game in a long time, man. I gotta get back on my game. I used to play a lot of Mortal Kombat. A lot. Mortal Kombat 9. Yeah. I think I stopped at 10. And then I played a lot of Smash Ultimate. Anyways, we just started. So today we're going to be going over the metabolic map. This is the single most difficult lecture in biochemistry because it's not in the book. And most of what I'm going to put up on that board comes from memory. And my memory might fail me at certain points in time. I have a couple slides that I prepared while we were answering one of the questions beforehand. But a lot of you might know the content better than I do at this point. And there will come a time that you don't need my help. I just had a conversation with a student yesterday who was like a month out from their test and they're scoring well and they got a 131 on biochem and this and that. And they're like, what else can I do? And I was like, why the hell are you asking me? Like, I don't know, ask someone else. Or why are you asking anyone, to be honest? But this is a lesson really for those people who are all the way at the tail end of their prep and they want to see the big picture. So what are the goals of this lecture? The goals of this lecture are to have a holistic understanding of the way that everything within the cell matches up with other things in the cell, other things that happen. How do they turn one another on and off? So that I know that if a passage gives me some specific point about the cell, that it says that there's a lot of ATP in the cell, or there's a lot of NADH in the cell, or they say that there is blah, blah, blah being produced by this pathway, I know what other pathways are on at that time. Specifically, as it relates to cellular responses to endocrinology. And this is more so the chapter 12 bioenergetics sort of lecture that we have in biochem that you've probably seen before if you've watched my biochem videos. This will not be a long lecture. It is just straight information. There's not much room for interpretation here. There's not a lot of room for like, what if it's posed like this? What if it's posed like that? Will you, and this is where people start to get lost. Will you ever get a question about this on the MCAT? This whole thing? No. Is that the point? No, that's not the point of this lecture. The point of this lecture is to take a seat, look back, and see, do I know everything that's going on the board right now? And if I don't, what is it that I don't understand? This is more of a self-reflection lecture than it is anything else. Are you guys ready? Okay. Some people who were not here last time when I talked about where we begin, who was here who knows the answer to that question? Where do we start with the metabolic map? Did you guys hear me last time? You guys were in the room. Where do you guys think we begin? Where does everyone else begin? Everyone starts with what? Everyone starts smack in the middle of the board. They put down glucose. Right? Alpha or beta, this one? Alpha or beta? Confidently, someone. Beta. Everyone throws glucose up on the board. That is a major flaw. This guy is going to go over here. Okay? He's like the progenitor of everything that's going to happen downstream. Like, can you go backwards from here? Is there any place to go back? If you go back, you're going to go into mechanical and physical digestion and like absorption, whatever it is. And I'm not trying to do biology. I want to do biochem. So I need to start at a point that is strategic so that I can go back and forward and see what pulls what in what direction. What is that starting point? Acetyl-CoA. Acetyl-CoA is the player in biochem. All right? Who has a coin? You don't have a coin? Or you can look up flip a coin on your laptop. Heads, we go backwards. Tails, we go forwards.
Heads.
We go backwards. Where did acetyl-CoA come from? Now, if you guys at home can watch this on a TV, I recommend it. Because I'm going to need to concentrate my writing very hard. And if any of you guys are comfortable enough to come and stand over here in the back if you can't see anything, I don't care. I don't care where you guys can sit on top of these tables for all I care. But we're going to be concerting my writing quite a bit. I just hope that you can see. All of you guys at home, put this on like a projector. All of you rich people with like theaters in your houses, go watch it there.
Do you want fine lines?
Huh?
Do you want my fine line?
What's that?
The expo?
Oh, we have. Yeah, we have.
Oh, right, they're in there.
That's a good point. Where did acetyl-CoA come from? Pyruvate. This is pyruvate. Turns into acetyl-CoA through activity of what? I need different colors. Enzymes will go in red. Pyruvate dehydrogenase complex, PDH. What is the byproduct of the action of the pyruvate dehydrogenase complex on pyruvate? What comes out? We put stuff in, stuff comes out. We lost a whole carbon. CO2. That's where your first carbon is lost. Because remember, when this goes forward, we're going to lose both these carbons inside of the cycle that's going to go into. But we lose a carbon before we go into there. So the CO2 gets lost. We also gain NADH and H+. And this happens through a series of enzymatic steps within the pyruvate dehydrogenase complex because it has a lot of coenzymes and cofactors. You have to remember in medical school, tender love and care for Nancy. Right? TPP, I think this is lipoic acid, something like that. And then you have acetyl-CoA, or coenzyme A, which is going to make acetyl-CoA. So the coenzyme A turns into acetyl-CoA, sorry. FAD and NAD, right? So these are your 5 sort of things that go into the pyruvate dehydrogenase complex. I'm just going to put that right here. Tender love and care for Nancy. TLCFN. You can look that up and everything will come up, right? Do you need to know that? Not necessarily. I'm just doing that for completion's sake, right? Okay. That's the pyruvate dehydrogenase complex, right? Is that reversible? Is that reversible? No, can't go back, right? You can't go back from here. Where did the pyruvate come from? Phosphoenolpyruvate. This is pyruvate there, and this is enolpyruvate, where it would be OH. The phospho part comes from the attachment of a phosphate group onto that complex. That is phosphoenolpyruvate. The enzyme that turns phosphoenolpyruvate into pyruvate is known as enolase. It breaks the enol. And gives us back what? ATP. One of the payoff steps of glycolysis. PEP came from? You have to be able to do it backwards. PEP came from what? Well, how do we know how to move backwards? Track the phosphate. The phosphate's on the 2 position. And we oxidize this. The 2 position got oxidized into the enol. This means that we had 2 phosphoglycerate beforehand. This is when we start to draw things standing up. Two phosphoglycerate. Oh, I haven't been writing the names of these things. What color? How's brown?
Wait, isn't PEP to pyruvate kinase?
Oh, sorry. You're correct. My bad. See, I'm already messing up. Pyruvate kinase. I was wondering where the kinase was because I knew there was an ATP there. Thank you. And then this is enolase, right? This is enolase. What's next? Keep moving backwards.
Is it a mutase?
3-phosphoglycerate turns into 2-phosphoglycerate through the action of? Yeah, very good. Let me just do this. Yeah, like lost in my own head right now. Give me 1 second, guys. If you want to be very particular, I knew that there was something that comes out here. I just want to make sure. You can say that an H2O comes out of there, if you want to be particular. We said that the 2PG, I'll put the names up if we have the space. We said that the 2PG comes from the 3PG, correct? This is 3PG. We said phosphoglycerate mutase. Probably going to use this chair at some point just to get all the way up there. The glucose might end up over there. Please keep track of where I'm at on the board. All right. The 3-phosphoglycerate came from 1,3-BPG. BPG. What gets made? This goes ADP, ATP, and this is phosphoglycerate kinase. Remember, when you have a kinase, it's a reversible process. We're going to label the reversible processes in a very bold marker so that we can actually see them, right? And that's also going to be important when we go through gluconeogenesis, right? Let's start going that way now. What's next? Yeah. So next, this actually came from what? What did that come from? What's it called? Like, what do we call that normally? Yeah, gap. And this enzyme is actually really important. Glyceraldehyde, phosphate dehydrogenase. You worm. There's a phosphate on there. You have NAD plus, and what else? What changed about the molecule other than being oxidized? We put a phosphate on there. So those both go on, and NADH and H plus comes out. The gap is in equilibrium with another thing, and they both came from what? Huh? Fructose 1,6-bisphosphate. This is where things get testy. No pun intended. Let me do that a little better. OH. Hold on. OH, OH, OH. Enzyme? Aldolase. Does both of these. DHAP I'm not going to put on the board because it's not super important. But know that TPI controls the transition between the two of these. Triose phosphate isomerase. I'll make notes about these as well as we go throughout the lecture. And I want you to do your notes the way that I do them. Where if you're doing it on an iPad, which most of you are, you're going to use a different color and put a star next to it or highlight it or something. And somewhere on the next page, you will draw your notes in that color so that you color coordinate which notes go to which part of the diagram. So when I tell you that when triglycerides break down and give you glycerol, you can oxidize the glycerol into glyceraldehyde and it can enter the glycolysis cycle at this point. I'll put a pink star over here and you'll write what I say in pink. Does that make sense? Very good. You see why this is a complicated lecture? It's a little bit difficult to follow. You guys are okay? 3 people already left, so.
What's the enzyme on
The
the top arrow?
top arrow, aldolase, does both of those
Oh, both of them are on those. Okay.
at the same time because you're breaking it into 2 3-carbon components. Yes?
Are the structures super important?
Would you like to sit here?
I can see it.
Okay.
I like that. But are the structures super important as well, or is the bigger picture just the...
Are the structures super important? I believe it is important to recognize what part of glycolysis you're at by a general structure. If you don't know exactly where everything goes, that's okay. But I want you to look at a 3-carbon sugar and be like, I'm probably in the payoff phase of glycolysis. I want you to be able to look at fructose and glucose and be like, I'm probably right at the beginning, right? And from there, you can really use some facts about the different types of sugars in order to figure out exactly what you're looking at. So if you see a 6-carbon aldehyde sugar, more than likely you're looking at glucose.
I think they really like asking how many carbons
Yes.
are on in these pathways.
Yeah. So they really like to, this is called carbon counting. They really love to ask you if you know how to carbon count, right? By the way, the reason I'm leaving this empty is because underneath glycolysis, we're going to fill this with more pathways. So like, just be mindful. There's a reason I'm doing everything. I've never actually given this lecture before. Like I've given it in like tutoring sessions and things like that, and I've like narrated it, but this is the first time I'm putting it to paper, or I guess whiteboard. What's next? Fructose 1,6-bisphosphate came from? Okay. This, I'm going to leave a little bit of room, and I want you to do as well. How am I doing on space?
Good, I guess.
It's good? What do you mean you guess?
No, it is.
Someone who's more confident, please go look at the camera. Okay.
With how small you're writing, you're good.
Okay. Can I write bigger?
Yes.
Yes.
Okay. I can, okay, then I'm going to write bigger for this part. This is not like incredibly important. This is important.
Everything, like after we do this, we gotta make it smaller.
Okay. Okay. That is fructose 6-phosphate. The reason I put that in such bold letters is because this is PFK1. You guys hate PFK1. Despise. Okay? Eventually, you'll put another arrow here. Spoiler alert. Next, glucose 6-phosphate. I'm going to write this off to the side. I want you to do the same. Glucose is the aldehyde sugar. How do we draw glucose? Look at the thing. Thumb is the aldehyde. Flip off the board. You've got all your OHs at your fingertips, right? Your first OH is like your pointer finger going to the right. These two at the bottom are on the right, and the middle finger is on the left. Am I going too fast for you guys? Okay, good. Because if you said yes, I would tell you to watch the video at home. What is this? What isomerase? Phosphoglucose isomerase, PGI. Anything going on over here? No. No, there's not. This is very simply the two-step process of tautomerizing the aldehyde and then tautomerizing the other way. You do 2 tautomerizations and it hops the double bond. Yes?
I've seen it sometimes called phosphohexoisomerase.
You could do that as well. Hexose, yeah, like, it's okay. That's probably a more general one that's used for sugars throughout the body, because glucose isn't the only sugar that we have. Did I tell you guys why we have glucose as the major sugar in the body? It's because it's the most stable chair, right? If you draw glucose in certain configurations, think the beta configuration, everything's equatorial, not axial, right? Then this came from our good guy, glucose. Am I in frame? Good. I believe it is pertinent for you to know that the barrier exists here. That there is a semi-permeable barrier in most cells that is controlled by what channel? GLUT4. GLUT4 in muscle cells, and I believe adipocytes as well, right? My memory doesn't fail me. Someone please correct me on that. This is insulin reactive. You will be asked this many times, whether GLUT4 is insulin reactive or insulin independent. It is insulin reactive, meaning that the glucose cannot pass through the holes of that channel until insulin reacts with that channel, activates the receptor tyrosine kinase, very important. This is an RTK. Activates the cross phosphorylation domains of the RTK, transfers the signal over into the cell, and opens the channel for the glucose to go through. The insulin-independent pathway that is important for you to know is GLUT2. In what? Hepatocytes. And I believe pancreatic cells. Once again, check me on that.
Pancreas, liver, kidneys, and intestines.
Very good.
Oh, and you were right about the GLUT4 being in adipose.
Thank you. This is why I'm not going to teach next year. The information's failing me already. This is probably my last year teaching the content. I think I told you guys that before. Yeah. Like the entire breadth of the MCAT. Like I'm probably going to teach like specific lectures about specific things next year, but I'm not going to do like a full content overhaul. There's no point. I think people need more than that. So insulin-independent versus insulin-dependent pathways of glucose sequestration into the cell. Can the glucose 6-phosphate go back? No. We need an accessory pathway to hop over that bridge, correct? Of these, which ones are irreversible? PFK1 is irreversible. Next? Hexokinase is irreversible, which I didn't put on the board. Hexokinase, right? Which uses ATP, turns it into ADP. Very good.
Is it like a general trend that the kinase steps are typically irreversible?
Typically, until you get to phosphoglycerate kinase.
Isn't pyruvate kinase also irreversible?
Yes, it is. I said all of them are, except for that one. So for all of the ones that are reversible, why don't we throw down a reverse arrow? Should we do that?
Yeah.
Okay. Reversible, irreversible,
Would it be easier just to put like a benefit 0?
reversible. Remember, that's the same thing. Huh?
Would it not be easier for some of the other steps where this other stuff why not just on the back end?
Well, then where am I going to put all the cofactors and things like that? I want you to understand. You're going to do something with the cofactors. Trust me. I know what I'm doing. All right? This, reversible. This is reversible. This is reversible. This is reversible. That's not reversible. So hexokinase, PFK1, and pyruvate kinase. Only 3 steps, correct? Very good. On the reversible steps, since we're using the same enzyme, you just do that. Cofactors circle around the arrow, right? They swap through the arrow. So here, the PGK, right? When ADP turned into ATP going forward, ATP turns into ADP going backward. Where the NAD turned into NADH going forward, the NADH turns into NAD moving backward. Because you're using the same enzyme, right? except here. You are going to get the refunding of the ATP. Like you need to burn. Oh, guys, hold on. Yeah, my bad. I got tripped up. You are going to get the refunding of that ATP that you put in, right? But it's going to be used by a different enzyme. So we're going to use a different color for those arrows, and we're going to draw the enzyme in a different way. You guys see how I sort of spaced out the reversible step, the irreversible steps, so we can philosophize on them a little bit? Oh my God. Huh?
He has a method.
I do have a method. So that's glycolysis. What do you guys want to do next? You guys want to do escape pathways of glycolysis? Where are some places that glycolysis escapes? Let's say, what's your question? You could do the entire digestive pathway if you want. Let's do escape pathways of glycolysis at the end. Let's talk about the normal pathway of cellular respiration first. Where does the acetyl-CoA go? Krebs cycle. Where does the Krebs cycle take place? In the mitochondria. How does it get into the mitochondria? Yeah, it like transfers it through, right? So there's a little barrier right here. Right? Also from this step, you're not going back. It's not happening. There's no way to get the acetyl-CoA to turn back into the pyruvate. From here, the acetyl-CoA is doing so. This is why acetyl-CoA is really the main player. Once you make it, you're really never going. Like people say, it's like, oh, you know, glycolysis, you make pyruvate and then you don't go back. But you do go back, right? Like they're kind of lying to you. Like you kind of do go back. Here, you're really not going back. Like we are never, ever, ever getting back together, right? So let's continue down the normal pathway of what happens to pyruvate. Or sorry, acetyl-CoA. My bad. Acetyl-CoA can enter into the citric acid cycle through incorporation with, I'm going to do a curved arrow, something known as oxaloacetate, which we will draw at the end because I want you to see how this happens. The enzyme here is known as, not yet, citrate synthase. I'm going to explain in depth how every single step happens. Citrate has how many carboxylic acids on it? That's why it's called the tricarboxylic acid cycle, the TCA cycle. Mind-blowing, right? The important part of citrate right now is this part right here. I'm going to highlight the important part of the molecule that you need to follow. It's this part right here. This is citrate. I know there are no names. We'll put them at the end. It's okay, right? If we can. If there's no names, I don't know, figure it out. Whatever. I don't care. This is citrate. Citrate will turn into isocitrate, going through a transition with aconitase, right? The isocitrate isomerizes that OH position, correct? The OH has now successfully hopped onto this position, making it, and if you're going to take some notes next to these, I want you to know that this step happens in order to activate the compound. But remember right here that the leaving group, CoA, releases energy in the form, releases energy from its thioester bond. Remember that we had the thioester, which is one of our carboxylic acid derivatives with a very high energy potential right there. It's actually all the way at the top of the list. So turning the thioester into the carboxylate releases a crap ton of energy. And that release of energy allows you to slam the two molecules together, which would normally be very difficult. Right? This is how citrate synthase gets its energy to do this. Right? We have aconitase. Here, the isomerization sets up for oxidation and later thermal decarboxylation. Thermal decarboxylation, correct? Because remember that the thermal decarboxylation requires you to have a ketone that is beta to our carboxyl group, correct? And what do we see in citrate? We see a OH that is about to get oxidized that is alpha beta to that carboxylate group, correct? Good. So the thermal decarboxylation takes place along with a, what did I say? Oxidation. The oxidative enzymes in this process are known as dehydrogenases. So the enzyme that oxidizes isocitrate is known as isocitrate dehydrogenase. Guys, what's the rate limiting step of the citric acid cycle? Isocitrate dehydrogenase. Do you see why? It's because we are oxidizing the molecule and removing one of those CO2s. We're really not going back. We're not going to slam that CO2 back into the molecule. And also, like, just cuz. Isocitrate dehydrogenase. Rate limiting step. PFK1. Rate limiting step. This happens through the addition of NAD plus turning into NADH and H plus and the removal of CO2. You guys get that? Good. That means that as this leaves and we oxidize that, just draw out the backbone again and do everything we just said. Draw out the backbone. Don't draw the middle carboxylate. We have our two carboxyl terminals and an oxidized secondary alcohol, which turns into a ketone. I'll let you into a little bit of knowledge from medical school. The next enzyme, and anyone who can figure this out, you're quite astute. The next enzyme and the pyruvate dehydrogenase complex are sister enzymes. And I want one of you guys to tell me why when you look at the reaction. This is known as alpha ketoglutarate. Alpha ketoglutarate. Glutarate is that dicarboxylic acid backbone that you have. Alpha ketoglutarate will get oxidized, correct? By alpha ketoglutarate, AKGDH. Once again, NAD plus, NADH and H plus. Here we make what? Succinyl-CoA. Can anyone smart tell me what happened here and why I said that pyruvate dehydrogenase and alpha-ketoglutarate dehydrogenase are sister enzymes? They add CoA, but what else do they do? That's the obvious part. They added the CoA. Do you see how the terminal, the CO2 was released. In what process? If this was a beta decarboxylation, these are known as alpha decarboxylations. And whenever you do an alpha decarboxylation in the body, you need a cofactor known as TPP, thiamine pyrophosphate. But you will also need lipoic acid, CoA, FAD, and NAD. This is one of the tender love and care for Nancy enzymes. The same way that pyruvate dehydrogenase needed all of these cofactors, the NADH in this came from these cofactors. The same ones that we put into the pyruvate dehydrogenase complex, because these are the cofactors that you need in order to do alpha decarboxylations. Alpha decarboxylations are very difficult to do. Your body found a way to do them with these cofactors. So instead of NAD, now that you know that, I'm going to say tender love and care for Nancy. And you know that the N in tender love and care for Nancy stands for NAD+. Why does the NAD take the electrons, not the FAD? It sets up for a higher energy transfer in the electron transport chain. Remember that the NAD gets you how many ATP per NADH? 2.5, whereas the FADH gets you 1.5. Very good. You guys following? You guys seeing the math here? You guys are seeing the flow? So far, we're just doing glycolysis. This is like day 1, chapter 1, carbohydrate metabolism. This is not hard yet. Yes?
Are you adding stuff to the side of?
We're going to go off that way. Yeah. We're going to take this and move this way.
Okay, but you're not gonna go like.
No, not that way.
Okay, thank you.
We are going to go this way, but we're not going to go that way. Because here, you can imagine we're going to put our acetyl-CoA stuff. You look so sad. You look so defeated. How you feeling, man?
Yes.
Yes. You're feeling. The fact that we're feeling is good. 3 people already left, so.
I give someone a ride. It's the only reason.
Here, the alpha decarboxylation with tender love and care for Nancy cofactors, thiamine pyrophosphate, lipoic acid, CoA, FAD, NAD, sets up thioester bond. And you best believe when you set up a thioester bond, you're preparing for what? An energy transfer. That's what you're preparing for. You're preparing for energy to be transferred in a specific fashion, right? Remember acetyl-CoA? We set up for the energy transfer to slam it into another molecule. Or we prepared it for energy transfer to produce energy storage molecules known as fats, right? That's the other way this is going to go. Spoiler alert. This is succinyl-CoA. This process is named after the reverse reaction for whatever reason. This is modulated by what? Succinyl-CoA synthetase. Or sorry, hold on. It's synthase. No, synthetase. Synthetase. What's the difference between a synthase and a synthetase? It's the same thing as the difference between a kinase and a phosphorylase. ATP, or some sort of energy source, right? The synthetase uses ATP, or GTP, or TTP, or UTP, or CTP. The synthase does not. The way you're going to remember this is what? What's it called? It's called ATP synthase. Would ATP synthase use ATP? No, it would not. It wouldn't use ATP, it would make ATP. So you have a synthetase, it's going to use ATP, or some energy. Pause, though, because you're going to see that this synthetase creates. Why? It's named after the reverse reaction. Succinyl-CoA synthetase, named after the reverse process, because biochemists hate you and hate everything about you. So when we take the GDP and the PI and we incorporate it into the enzyme, we get GTP output with the formation of succinate, correct? Yes? Very good. I love giving this lecture. Like, I've only ever given it in like a private session before, but it's so much fun. No, I really enjoy giving this lecture. I hope that someday, I really do hope that someday, like you guys succeed and you guys do great and you guys do well for yourselves, whatever it is. There's no way you'll make it through medicine without teaching someone. And I hope that you aren't one of those people who just despises teaching. When you taste the sweetness of someone understanding something, it's different. When someone comes to you and they say, I spent years trying to figure this out, and you said something for 20 minutes and made sense with me. That's a different feeling. It's completely different. Alhamdulillah, it's fantastic. It's really nice. You guys need to feel that at some point. And you'll feel it when you have kids, like for sure. If you don't feel it with other people, you feel it with your own family. But doing it for like hobby is different. This is fun. I love doing this. This is actually my favorite part of my week. Teaching. It always has been. It's going to be really sad to leave this behind when I go to residency. But then again, I'll just be teaching medical students, so. Succinate. Succinate needs to be, now everything that happened here, right? Like this is just, the reason for this step is energy transfer. Oh, and I forgot to say that the CO2 left over here. Energy transfer, right? I'm going to outline where our CO2 is left right here. And now whatever carbons you put in have now gone out. That's why it's called a cycle, right? Is she crying? Did she leave to go like sob? Allahu Alam, you know. Arabic phrase of the day. Allahu A'lam. God knows best. Literally, linguistically, it means God is the most knowing, but it means God knows best, right? Allahu Alam. Succinate will turn into fumarate, right? Fumarate. Now, why, when we're doing NADH, and we're trying to maximize the amount of ATP that we get out of this, why is there a rice grain in my pocket? There is an uncooked grain of rice in my pants. I'm a paka brown guy, man. Like I swear. Like proper brown guy. Like honestly, this humbled me, man. This is beautiful. Look, I'm not lying by the way. Like look. It's a literal raw grain of rice. And I think, you know what? I think I know where it came from.
You can't take the brown out of you.
That's beautiful. No, that's like a metaphor. Huh? Explain why it's there?
He wants to know why it's there.
No. Fumarate. I will explain the TCA cycle instead. You get one or the other. Either you get this or you get the rice grain, okay? Like,
Why is the rice grain black?
it's in my pocket. And I have ink on my hands.
What have you been doing to the rice grain?
Get the hell out of my class. Yo, guys, I was walking up here. You guys did not lie about the brown, like the campus is open again. There's so many brown people. There's so many. Dude, I walked by a room downstairs, like the big lecture hall. It's just lines and lines and lines and lines of my brethren. And I think it had to have been like some sort of CS class. It was all men. Just men.
Did you think the demographic of like your class now was just like because you're brown?
Maybe we had the one white guy and then like two white guys. I grew up in like a 96% white community. So like I am not like, why do you think I sound like this?
No, like I know, but it's just like terrifying to imagine.
Yeah, I grew up in like a 94 to 96% like white Protestant and Jewish community. And like it wasn't uncomfortable like at all. I actually didn't face a lot of like racism growing up, to be completely. If anything, people were more racist towards me in the Middle East than they were in America. Much more racist. Much more racist. Anyways, fumarate has this double bond in the middle. And now we're using NAD. You would expect that all of our oxidations are done with NAD so that we can actually maximize the amount of ATP that we get out at the end, right? That's not the case here. And there's a specific reason why that's not the case here. Does anyone remember? Well, yes. So the enzyme here is what? Succinate dehydrogenase, succinate DH. Don't do it. I'm gonna leave that just for him because I know he's just gonna be giggling the whole time, like for the rest of. I've effectively reduced him to a child. Okay. So suc DH will take succinate and turn it into fumarate, correct? That double bond in the middle is actually special. That double bond is very special. And it tells you something about the nature of these bonds in chemistry. What do you think is more stable? A bond between two things that are the same, or a bond between two things that are different? Well, the same, because you don't have that sort of polarization of that charge that's going in both directions, right? That bond isn't actually pulling itself apart. Who's dying out there? You guys all right? Holy crap.
I'm so sorry.
Well, if you were sorry, you'd shut the hell up. Okay. Succinate has this carbon-to-carbon bond that we're oxidizing rather than the previous carbon-to-oxygen bonds, right? Those carbon-to-oxygen bonds are a little bit more difficult and require a bit more energy and can give more energy off when they get oxidized, in the sense that you are creating ketones and aldehydes and carboxylic acids and blah, blah, and this and that. But here you're really just creating a carbon-to-carbon double bond. So the amount of energy that you're able to extract from that is not as high, which means that you don't get as much energy output from it. Not only that, but I said that the carbon-to-carbon bond is a bond between two of the same atom. And when you have the same atom, you use FAD. This is known as a homooxidation. Whereas this was known as a heterooxidation. Don't start. All right? Between this and that, like, don't start. No, I can't.
You set yourself up for that.
I got a picture of it, don't worry.
Okay. This succinate dehydrogenase is a component. This succinate dehydrogenase is a component of what complex? Complex 2. And now this actually ties into the idea that I said before, that the complex 2 actually doesn't pump electrons. Why? We didn't get enough chemical potential energy out of the oxidation. The bond that we oxidized did not have enough chemical potential energy inside of it to pump electrons, right? Does that make sense?
It's because it's 1.5 instead of the 2.
Exactly. So this is the reason that you get 1.5 instead of 2, because like you're still helping with the whole process, but you're not generating enough of a proton motive force. There's two things that produce the energy. Number one, the reduction of the oxygen at the end of the chain that we talked about in the whole like battery sort of thing. We'll talk about it again, right? But number two, the fact that when you have the transfer of electrons from the FADH to the QH2, how favorable is that process and how much energy gets released? Is it enough to take hydrogens against their concentration gradient? It's not. Yeah. And remember that the difference between the concentration inside of the mitochondrial matrix versus the intermembrane space is actually logarithmic. There is 10 times as much hydrogen, protons, inside of the intermembrane space as there is inside of the matrix. Literally 10 times. So imagine you are playing tug of war, right? And you're pulling, and 10 clones of you are pulling on the other side. How are you going to win? You need a crap ton of energy. That's why these electron transfers are taking place, correct? Right. This fumarate is going to be broken into another compound known as malate through an enzyme called fumarase. Malate dehydrogenase doesn't come in yet. And now what is this doing? These two steps actually accomplish one thing. This allows for formation of bond that will reform, not reform, but reform OAA, oxyl acetate, right? And I personally never really remembered the structure of oxyl acetate. I always had to think of it as malate and then move forward, but I'll give you a little trick to remember OAA. All right? So now finally the malate can rest and everything can start over. We have by the way, over here, the enzyme name is fumarase, right? I'm drawing on the outside. Fumarase. And we have what going in? H2O. Whereas, and this makes sense because the backwards reaction would be a dehydration synthesis of the double bond from an alcohol. Remember that from organic chemistry? So to break that double bond, we can add in the alcohol and hydrate across that bond, right? Now the malate gets oxidized, and we're oxidizing a hetero bond, which means we're going to use NAD, right? So we take NAD plus, NADH and H plus, and that is going to make OAA, which looks like this. Make sense? What do you need? What's up? Why are you asking her? Ask me.
Is this why it's known as like a true cycle because it
It literally reforms exactly what you start with. That is OAA. What's up in the middle? What do you need? Okay. Just being weird?
Yeah.
Okay. At least you're not those people, right? We lost another one. We lost another. Like 6 people are gone. I just want to make sure that like no one's having a mental breakdown out here. Oh, malate dehydrogenase is the final enzyme here. Malate dehydrogenase.
Isn't there another one?
Hmm?
There's another one, right?
Is there?
See something.
Is there another enzyme, guys?
Oxaloacetate.
OAA is the final product. Shh, guys.
Malate dehydrogenase. Oh no, that's not the enzyme.
Oxaloacetate is the final product.
After malate, there is I can't pronounce it. Oxaloacetate.
Yeah, but that's this.
Oh, okay.
This is OAA. Do you guys want the names for this one? I know glycolysis we go through a lot, but do you guys want me to label this one?
Yeah, that would be fine.
Okay, let's label this. This is citrate. This is isocitrate. This is alpha ketoglutarate. Succinyl-CoA. Succinate. You know what? Just for your pleasure. Succinate. Fumarate. Malate. And OAA. If you were to look at the overall reaction here, what's really happening is that OAA plus A-CoA makes citrate. Citrate will turn back into OAA through the release of GTP, NADH and H+, 3 of them, FADH2. With the input of GDP and PI, H2O, 3 NAD+, and FAD. Did I miss anything? And the removal of 2 carbon dioxides. Yeah. We're going to put the electron transport chain right here. Yeah. Did that catch you guys off guard?
Yeah.
Too bad. You guys want a better place to put it? You guys want to know where you should put it? I want you to link this into the electron transport chain.
Okay.
So that this lines up with your complex 2.
Mine looks like,
But I'm going to put it here. Huh?
mine looks like little vapes.
Vapes? They do look like vapes. Hold on. Look at that, guys. We're smoking on that TCA pack. By the way, if any of you guys vape, like having an addiction to smoking, like very difficult, very hard, totally understand. Maybe you rolled with the wrong people at some point. Who knows? Like that is totally fine. If you guys are going to medical school, like actively pursuing medicine, blah, blah, this and that, and you vape and have no plan on quitting, you're dumb. Really dumb. I think people like these days, like I know people smoke, like that's fine. Addictions are addictions, whatever it is. But if you smoke and you have no plan on quitting, like you're stupid. My 2 cents of the day. Usually the next question is, wait, but what about? Hookah Lounge is a Jahil place, man. You guys remember that word? Jahil. Ignorant. Jahil means an ignorant person, but ignorant in like a religious sense. Okay, what should we do next, guys? ETC? Let's do it. The electron transport chain is established between two layers of the mitochondria. Guys,
This may sound dumb, but is the way you drew the structures like?
just to differentiate between them.
Okay.
This is complex 1. Complex 1 takes what and transfers electrons onto what? You take NADH and H+, don't forget your H+, and you make NAD. And out, I'm going to go in this way, out that way, up the top. And you're going to transfer this with Q and turn it into QH2. Yeah? This pumps protons. Because we're going to do this. I'll explain this in just a second. Everyone just relax and copy this down somewhere on the side of your page. And leave space. The FADH2 through succinate dehydrogenase, which is a part of the complex 2 attached to that complex, right? Will transfer onto QH2. Yes? This does not pump protons. Because the difference in reduction potentials of FAD and Q is not large enough to get that energy output. Because remember that delta G is equal to negative NFE. So the favorability of the reaction and the amount of energy that's going to be released through its stabilization and transfer is dependent upon the E. And we're talking about E cell. And that's reduced minus oxidized. The reduced thing is being the Q. The oxidized thing is being the FAD. This is like, let's say 3, and this is 2. You only get 1. Whereas opposed to this, you get 2, right? So the larger gap between the reduction potentials of the NAD and the Q release more energy when you transfer onto Q. NAD would rather be oxidized. Q would rather be reduced. Does that make sense? You guys get that? Redox, right? I feel like that was a pretty comprehensive lecture. A lot of you guys were here for that one, right? Then above this goes the cytochrome C, and above this goes the oxygen, which is why it's the final electron carrier, correct? Yes?
The way that the FAD goes back into citric, the crabs,
Remember,
the NAD do the same?
that like floats around, sort of, but like there's shuttles and things like that we're going to talk about. Remember that the succinate dehydrogenase is attached to complex 2. So when the succinate comes and turns into fumarate, you get the production of the FADH2 inside of here because the SDH is basically attached to the FAD. This FAD turns into the FADH2, which immediately transfers onto Q, which gives you QH2, and this goes back. You guys see how it's sort of like cycling inside of the complex, right? Very good. Believe it or not, this is an off day for me. I feel like I'm not that sharp on my feet right now. You'll get there, I promise. And if you don't, it's okay. You always look so concerned when you're here.
I feel like everybody says that. I'm good. I'm excited. I'm ready.
My learning pace is just very
Pumped is an interesting adjective.
pumped.
Yeah. I want to enjoy the lecture too. The QH2. What?
Why don't we just like spray cologne?
Do you know how many times I apply cologne throughout the day? I want you to guess. Let's say I'm awake for 18 hours in a day. How many times do you think I put cologne on?
She has a guess.
Yes.
No, she has a guess. She said 6, 7.
That's not that far off.
I'm assuming every 2 hours.
But it's also because like I usually do one before every prayer. Usually.
How many bottles of outlets have you gone through?
This is my second bottle.
Only?
Yeah. But like this is my second bottle and you can feel how empty it is.
Oh, what the heck?
Shake it.
Dude. How'd you get the... You know what? I'm not going to ask that question.
QH2 will transfer into complex 3 and undergo a process known as the Q pool. I'm not going to show the whole Q pool, okay? All you need to know is that the QH2 is going to cycle back into Q. I'm not showing you that it's going back to complex 2. It's just going to turn back into Q and get recycled both ways, right? And the QH2 is going to cycle its electrons from cytochrome C in its oxidized state, cytochrome C ox, into cytochrome C reduced. Cytochrome C ox, bigger, zoomed in photo of what I'm showing you. The QH2 undergoes a very complicated process called the Q pool, by which the cytochrome C ox turns into cytochrome C reduced. There's no real way to differentiate between them. One of them's reduced, one of them's oxidized. This will turn back into Q. This process right here is known as the Q pool. And it is where you have intermediates. There are intermediates that you go through, like the Q radical anion. The Q radical anion. And whatever else. The QH blah, 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 something, whatever. That's what I'm showing here. So what I'm not showing you here is the Q pool. It's not super important, right? Just know that it's there, because they are going to ask you about that. This is a very favorable reaction. Favorable reactions will pump protons.
It's like, I know you didn't draw it that way, but it's usually drawn with like the CoQ inside C subunits, right? Is that like...
I don't care. I don't care about all the subunits.
Okay.
I don't.
Is it...
I'm going to comment on the FMN and the iron centers and everything. I'm going to do that in a bit. Cytochrome C red turns into cytochrome C ox, and O2 gets reduced into whatever it gets reduced into, to eventually catch the protons that come down. C4 pumps protons. And I'm not going to draw this going up, actually. I'm going to draw this coming down. Just say it's like that. Now, the pumping of protons has created a massive proton motive force over here, which is now pushing against the turbine of ATP synthase, right? Is O2 minus, superoxide, OH minus, like all those sort of exist all together. I just put the minus sign there. I want you to know that the oxygen's been reduced.
Oh, but you're drawing it just like bouncing off, right?
Yeah. It's picking up the electrons and coming back. Because what I want you to know is that these hydrogens will flow through ATP synthase. And that flow through ATP synthase resolves the difference in concentration between the intermembrane space, the IMS, and the matrix down here. And that resolution allows for you to do what? Allows for you to turn the turbine of ATP synthase, which will take ADP and turn it into ATP, and eventually these hydrogens will link up with water to make H2O, such that for every single glucose molecule, you will get These are the oxygens we're using. 6 CO2 and 6 H2O. And I think it's 32 to 36 ATP, depending on what source you use. Where does the ETC happen? Along the inner mitochondrial membrane. Where does the citric acid cycle happen? If I could put this whole thing in here, I would, but I wanted to associate them so that you know they happen in relatively the same place. This is the reason that succinate dehydrogenase is associated with complex 2. Does that make sense? Let's do a little bit of record keeping. You know what? That'll be the end of part 1. Thank you guys for watching. Check the links in the description below for support, and I'm literally going to record part 2 right now. Bye. All right, welcome back. Part 2 of the metabolic map. Let's continue. So we left off with the electron transport chain. Now we're going to do these sort of ancillary pathways. And in order to do the ancillary pathways, we need to know a couple of tidbits of information about these different enzymes, right? This is where we're going to start to get into the nitty-gritty biochemistry. Right, the nitty-gritty biochemistry. 1 second. I don't want to do this wrong, so I'm going to look it up. First, this whole thing was kicked off by insulin. Insulin after meals, you get the detection of high glucose entry into liver and pancreatic cells, which releases insulin in response to the activity of glucokinase, which has a higher Km than hexokinase, which means that it only gets activated when glucose levels are high. So a high level of glucose leads to the release of insulin. That insulin activates the GLUT4 receptor to bring the glucose into the cell, gets trapped as glucose 6-phosphate because of the fact that we have glucose transporters, not glucose 6-phosphate transporters. Once the glucose is inside the cell, you either turn it into immediate energy in the form of ATP, or you turn it into long-term energy in the form of fats and glycogen. Okay? The body splits this up into 3 distinct pathways at 3 distinct points in a beautiful way. Number 1, the primary pathway is to move forward to the production of energy. That's the first thing. That the glucose 6-phosphate that's made will immediately shift the equilibrium of phosphoglucose isomerase into fructose 6-phosphate. Because Le Chatelier's principle is dominant inside of the body, right? This was a discussion I had yesterday with some of my students as well. And Le Chatelier's principle is one of the most important principles in biochemistry, right? So the moment we make the glucose 6-phosphate, it's looking to disappear by Le Chatelier's principle. We push this forward to the formation of fructose 6-phosphate. You have a little bit of a stall right there because of the fact that you have a rate-limiting step coming right after. What activates the rate-limiting step? What's the most important thing? What does it make? Fructose 2,6-bisphosphate. PFK1 is activated by fructose 2,6-bisphosphate. And we have that activation through the production. I don't care if you can't see me I'm not the important part here. You get this through the activation of a specific enzyme in the insulin pathway, which we're going to talk about right up here. Okay, right over here. The fructose 2,6-bisphosphate came from this process. We have inside of cells a bifunctional enzyme. And this bifunctional enzyme has a FBPase2 domain. And linked to that, we have a phosphofructokinase 2 domain. I incorrectly said that this is only in liver cells before. That is not the case. Okay, this is in liver and muscle cells. Does that make sense? Make that arrow a little shorter. When you have the presence of fructose 6-phosphate inside of these cells, along with the activity of insulin, which activates the kinase domain, you get the attachment of a phosphate from ATP. Let me do this a little earlier. onto the 2 position of the fructose. The question you may be asking yourself is that the 2 position is currently occupied by a ketone. How do we phosphorylate a ketone? The 2 position is occupied by a ketone in the straight chain form of the sugar. When you cyclize the sugar, that ketone breaks into a, what does it break into? You guys remember that when you cyclize the sugars, when you cyclize glucose, it makes a hemiacetal on the anomeric carbon. This will turn into a ketal, a hemiketal, right? Or a ketal, because you have R going in both directions, right? I'm not sure. I haven't looked at fructose in a long time. But you cyclize this, and then you phosphorylate it. That fructose 2,6-bisphosphate is the most potent activator of PFK1, which is going to push forward this process. And that makes sense because the activity of insulin inside of liver and muscle cells is what's going to produce the fructose 2,6-bisphosphate from fructose 6-phosphate, which is now in massive amounts because of the activity of hexokinase and pushing forward to this side of the equilibrium. So as to not stall the reaction, we create massive amounts of this to activate the PFK1. PFK1 pushes the reaction forward. Does that make sense? That this is the primary way that we get the phosphates over to the other side. And that's also why this isn't that this isn't reversible, so we don't come back this way. And we don't have other escape pathways, which you know we have some pathways that we're going to talk about going this way as well. Cool. The FBPase2 domain is activated by glucagon. And what that's going to do is going to take fructose 2,6-bisphosphate and turn it back into fructose 6-phosphate. And that is going to inherently reduce the amount of positive activation that you have. The activation of PFK1 will go down, which will slow glycolysis, because in the presence of glucagon, we're going to prefer what pathway? We're going to prefer gluconeogenesis, which is the reverse reaction which we need a different enzyme for, correct? Does that make sense? What else is going to increase the activity of PFK1? It is also going to be increased by what I call a low energy status. What do I mean by the low energy status? What I mean by that is if the end goal is making ATP, and we make most of our ATP from ADP, we can actually create, other way around, an ADP to ATP ratio. Actually, no, sorry. An ATP to ADP ratio. It doesn't really matter which way you think about it. If the ATP to ADP ratio is high, that's telling us that there is a lot of energy inside of the cell. That's telling us that we've created the ATP and we have met our short-term demand for energy. Does that mean we need to create more energy, or do we need to start pulling back on the reins a little bit? We need to pull back. But if this ratio is low, that is telling me that there's not enough ATP inside of the cell. There's too much ADP. That amount of ADP needs to be compensated for by energy productive pathways, which is going to activate PFK1. This is why you have that tender balance between the ATP and ADP. You're very tightly controlling how much is made.
Does somatostatin have a role in that too?
We're going to talk about somatostatin in a little bit. It is inhibited then by high energy status, and one more thing that we need to talk about. We are inhibited. Can you guys see the pink? Does it show up? Inhibited by citrate. Because if there's a lot of citrate in the cell, what was there a lot of? A lot of acetyl-CoA, which came from pyruvate, which came from glycolysis. So a lot of glycolysis has already taken place. And if we're moving into citrate, we know that we're already producing a ton of energy through the citric acid cycle. Do you see any breaks here? Do you see any points where this is going to go backwards? Do you see any points where this is sort of going to stop? Once you make a lot of citrate, you're rolling. You're going to create all of that GTP and NADH and FADH2 and turn that into ATP and blah, blah, blah. So the high citrate level is actually going to signal to you that we're good for now. Maybe you can slow down a little bit. That's inhibition. And the other thing is the high ATP to ADP ratio. That's also going to inhibit right here. When that inhibition takes place, listen to me very closely. when the energy demands of the cell are met and that inhibition takes place, we get a stall of glycolysis in the first quarter. The first quarter of glycolysis stalls, right? That leads to a buildup of fructose 6-phosphate, but an inability to move forward. Le Chatelier's principle says when we tip this way, we have to tip back that way, correct? We have to move back to forming what? Glucose 6-phosphate. The fructose 6-phosphate will take the reverse pathway to turn back into glucose 6-phosphate. Now we have a problem. The buildup of fructose 6-phosphate can't be alleviated by moving forward because these pathways are off, because we have high energy in the cell already. We've met our standard energy demands. Now, remember, I said we either need to have immediate energy production or we need to move into energy storage. We need an escape pathway that's going to allow us to turn intermediates in the beginning of glycolysis into energy stored products. What is that energy storage product? Glycogen. We are going to take the free glucose 6-phosphate and turn it into glycogen through a process called glycogenesis. Allow us to look at this. As the fructose 6-phosphate stalls and we reform the glucose 6-phosphate, the glucose 6-phosphate is going to escape into a pathway this way. And I'm going to say alt. The glucose 6-phosphate will begin to be linked together onto a protein known as glyco-what? Genin. Glycogenin is a core molecule on glycogen that the glycogen builds off of. Glucose 6-phosphate will turn into glucose 1-phosphate. This is not super important. If you guys don't want to write this down, it's fine. You can skip this, whatever it is. Then this will turn into UDP glucose. And that UDP glucose will turn into glycogen. The two important steps, if you guys want to skip this, it's totally fine. Just go straight glycogen into glycogen. The two important steps you need to know are right here. Number one, is that you have a first enzyme known as glycogen synthase. And glycogen synthase is going to create 1,4 bonds between the glucose. Meaning that when you have glucose head to head with another glucose molecule, they are going to link like that across. Whereas if you have a 1,6 connection, the 6 carbon of this one is going to link upwards to the 1 carbon of the next one. And do you guys see how this is chain and branch? Chain and branch and chain and branch and chain and branch. And you stack branches on top of chains, right? So first is glycogen synthase, and the second is branching enzyme. Branching enzyme. What's the rate limiting step here? Glycogen synthase. I believe. Someone quote me on that. Yeah? Branching enzyme is going to make your 1,6 connections. Alpha 1,4 and alpha 1,6 connections. 1,6 connections stack top and bottom. 1,4 connections connect side to side. So what happens is that you have a central molecule of glycogen, which is once again being produced in order to store the energy that is found within the glucose molecule after it's been converted into glucose 6-phosphate, because you can't send the glucose 6-phosphate back out of the cell. You need to store it in the cell somehow. What's happening is that you're making branch, chain, branch, chain, branch, chain, branch. And you get these terminals. And from those terminals, you can break off glucose molecules in glycogenolysis, right? and which we'll talk about later when we talk about the glycogen, the glucagon pathways, right? These allow for, you'll see this language on the MCAT all the time. Anyone who's taking the MCAT, you can quote me on this. Rapid mobilization of glucose monomers from the glycogen branch sites. Someone who's taken the MCAT before, yes or no? You've read that statement before? Rapid mobilization of glucose monomers from glycogen branch sites. Branch sites meaning the end of the branches where the chain continues. You just break them off immediately. So that big expansive branch with all the little chains coming off of it, you break off all those chains and then you debranch. And then you break off all those chains and then you debranch. Right? Does that make sense? So that's in glycogenolysis. If you guys haven't noticed, everything that we put on the board so far is under the control of insulin. There is not a single catabolic pathway on the board right now. Not one. We are going to do all of the insulin pathways first. Does this help to contextualize what happens in the fed state? Everything you see on the board is happening in the fed state. Everything, except for that, FBPase2 activation, which turns off glycolysis. Correct? We're almost done. I promise. The rest of it goes very fast. This is the chunk of the material. Oh my god, it's 9:16. Thank God I took a nap today. Because I woke up at 4:30. Anyway, it's been a long day.
I think this is the latest you've started lecture in a long time.
They're not open till 7. The new semester, for some reason, they didn't. So we're pretty good on time, to be honest. It's very standard for us, but I knew this was also going to be a very long lecture. If you guys have to go home, feel free. Not that you have anything better to do than to study for the MCAT. You're probably going to go home and do work anyways. Okay, so we talked about the escape pathway in the first portion, where you can pull the insulin, you can pull the activation of PFK1 because you get the inhibition from citrate and ATP, correct? So that's the way that you can pull that. By the way, is there any glare on the screen? I forgot to turn these lights off, like over here. No. Okay, we're fine then. You guys are okay. Next, what else can happen? What else can happen? Where else can we inhibit this cycle? Right here. We can inhibit this. And that inhibition is done by same thing. ATP, high energy production. And its upstream brother, alpha ketoglutarate, will inhibit that. So lots and lots and lots of alpha ketoglutarate will inhibit that. One more place of inactivation is here. It is the same thing, high ATP, high NADH. Once again here. When we get the inhibition in the citric acid cycle, that is going to limit the amount of acetyl-CoA coming in. The acetyl-CoA will back up. Question, does acetyl-CoA have a natural escape route? No, it doesn't. It doesn't have a natural escape route into any of the pathways that we've talked about already. So the escape route must be prepared and made for it, correct? What is the escape route that we're talking about? The escape route in the second half of glycolysis, after the energy has been produced by the payoff phase, after we've already done the oxidation, after the acetyl-CoA has been prepared, what we are, and think about this, what we are storing instead of the energy, the glycogen stores the energy held within the glucose molecule. The acetyl-CoA escape pathway is going to hold the energy held within the carbon to carbon bonds, and this thioester bond right here, which will later be reformed in an alternate pathway. What is the escape pathway of acetyl-CoA? What do we make from it? Huh? No, not yet. What do we make from it? Fatty acids. Yes, fatty acid synthesis. Fatty acid synthesis is very interesting. When the ATP backs up, when the acetyl-CoA backs up, we have an alternative pathway of energy storage rather than energy production, which is controlled first and foremost by the enzyme acetyl-CoA carboxylase, known as ACC, under the activation of, what activates ACC, guys? Huh? What activates ACC? Very basic MCAT question. What activates ACC? What do you think? Think about it very hard. Look at the board. Think about it very hard. Huh? It's one of the reagents, so it's not necessarily going to activate it. Insulin. Insulin activates acetyl-CoA carboxylase. Because of the fact that the energy productive processes within the body are controlled by insulin, and therefore the energy storage processes in the body are also controlled by insulin. Acetyl-CoA carboxylase will obviously take a CO2 molecule and put it on acetyl-CoA, giving you a molecule of malonyl-CoA. Yes?
Insulin activates both energy production and energy storage. How does it make it focus on energy production over energy storage?
That is a fantastic question. If insulin activates energy production and energy storage, how does it focus on one versus the other? How does it know when to activate one or the other? It doesn't. It doesn't. It depends upon which substrates are high in the cell and which aren't. Insulin activates everything generally. In the presence of low ATP, the activation of this pathway predominates. But once this pathway backs up, when the ATP is high, the NADH is high, and you have a backup of the acetyl-CoA and it can't escape into the TCA cycle, it begins to take this alternate pathway, which is already on. It's ready for it. It's like the couch is warm, right?
So basically excess energy is fat.
Yes. Glycogen and fat. You guys understand? Very good. You do not need to know a lot about fatty acid synthesis. There are two things you must know. You must know that we are going to add acetyl-CoA onto this, ... until it becomes a 16-carbon fatty acid known as palmitate. And you must also know that rather than using, because we're eventually going to have to do a reduction here in order to remove that double bond O, right? Rather than using NADH to do the reduction, it uses NADPH. There's a reason for this, and we'll talk about it in a little bit. So I'm just going to put NADPH and H plus right here. NADP plus. Is NADP the same thing as NAD? No, it's not. They're completely different things. It's almost like telling you and your sibling, who look very similar, but you're different people.
Is it just a phosphate?
The phosphate makes a very big difference. You can look up the structure. It makes a very big difference. Eventually, that palmitate, if you guys would like to know, will be undergoing an esterification reaction with, if anyone knows, that'd be a surprise. It undergoes an esterification reaction with glycerol. And the fatty acid plus the glycerol makes a triglyceride. And those triglycerides are stored as adipose tissue fats. That's where we burn our fats from. So the palmitate plus the glycerol undergoes an esterification reaction with the subtraction of H2O. So 3 of the palmitate is going to give you where all of these are palmitate. Doesn't necessarily have to be. You can also use fats that you pick up from the diet, right? But that's what happens. That's how you make triglycerides. That glycerol is important because that glycerol should remind you of something. Kind of looks like something, right? Looks like what you used to make soap, number 1. Use glycerol to make soap. And number 2, this guy, when you break fats down, we're going to see what happens. Because eventually you're going to turn this, when I break the fats down, I'm going to take this triglyceride and I'm going to break it down back into 3x fatty acid, and I'm going to turn it back into glycerol. And that glycerol, when we activate the reverse pathways, will actually come over here. And it will plug itself back into glycolysis or gluconeogenesis. It's a beautiful thing, man. So, the fatty acid synthesis, controlled by insulin, production of malonyl-CoA. A-CoA makes 16-carbon fatty acid using reductions by NADPH, which comes from where? Where does the NADPH come from? What about DNA? You're close. There you go. The NADPH comes from the pentose phosphate pathway. Why do we have NADPH in the cell right now? When all the energy is supposed to be going towards NADH and ATP production, blah, blah, and this and that, there is a pathway that you cannot forget about. That the glucose, what the hell? That the glucose can actually go into an alternate pathway. And this pathway will take the glucose and it will turn it into, here's the glucose 6-phosphate, and this will turn into 6-gluconolactone. 6-gluconolactone. I want to make a quick comment about this molecule. 6-gluconolactone is the lactone form of glucose. It's glucose 6-phosphate. 6-phosphogluconolactone, sorry. Someone look that up, the first step of the pentose phosphate pathway. Sorry, I didn't mean to snap at you. Anyone have it? 6-phosphogluconolactone, correct? 6-phosphogluconolactone. Six-phosphogluconolactone. That 6-phosphogluconolactone is a lactone form of glucose 6-phosphate. I want to make a quick comment about this. Glucose is what we know as a what sugar? It is an aldehyde sugar. It is a hexose. What else? What's one more word that you can put before? It's a blank sugar. It starts with an R. It's a reducing sugar. Why is it a reducing sugar? Because on the anomeric carbon, the OH is free. And this OH next to this oxygen right here in the hemiacetal functional group, that H is very liable to be stolen. And you can oxidize that. And in the ring form, you get the stealing of this, and you get a double bond. That is 6-phosphogluconolactone. Do you see how this is a cyclized ester? What is an ester again? OOR. It just so happens that the R connects into the ring itself. Do you see how that is a cyclized ester? A cyclized ester is known as a lactone. They ask you this question all the time. You will be asked to identify lactones. Not only will you be asked to identify lactones, you will be shown a molecule that can close in on itself with a ketone on one end or some sort of carboxylic acid derivative on one end and an alcohol on another. And you must know that reacting a carboxylic acid derivative with an alcohol will give you an ester. But since that alcohol is in the same molecule as the carboxylic acid derivative, that will make a lactone. It is inside the same molecule. Right? 6-phosphogluconolactone comes from the oxidation of the OH in glucose. That oxidation must be done by some sort of oxidizing reagent, correct? So the oxidizing agent, in this case, is what? NADP, which is going to give you the NADPH that you use for fatty acid synthesis. Does it not make sense that the production of glucose 6-phosphate from the entry of glucose into the cell via insulin will give you the NADP through the escape pathway that you then use for the other insulin pathway? All of it controlled by insulin. Everything. Insulin did all of this. Everything you see behind me, insulin did it. Everything. It's meticulously curated that way. Yes?
So the pentose phosphate pathway's main purpose is to facilitate all those.
The pentose phosphate pathway's main purpose is to make sure that we produce ribose in the high energy state of the cell because we can use that energy to make DNA and produce proteins and make sure that cell division happens properly.
But the secondary products go.
The secondary products go to help with this. Very good. The 6-phosphogluconolactone is produced by the enzyme glucose 6-phosphate dehydrogenase. And NADP plus is turned into NADPH and H plus, which goes off to fatty acid synthesis to assist in the formation of long-term energy storage inside of the cell. This 6-phosphogluconolactone undergoes many steps in xylose and this and that. Am I almost off?
You're right.
That's fine. This is the end of the board. That's okay. I want the end of the board to be right here.
Yeah.
Okay. This goes on and on and on, and the end product is ribose, which makes sense to make ribose at this time because the cell with a lot of energy will want to reproduce. It's like people on ecstasy. You know, like when you have a lot of energy, what's the first thing on your mind? Reproduction, right? So the cell with a lot of energy will want to reproduce. So this gives you the ribose that you need for DNA synthesis, DNA replication, for blah, blah, blah. This is that all of the RNA that you're going to make in order to create the proteins that you need energy to create because those are such energetically consumptive processes. Doesn't it make sense that insulin allows you to do that? The other thing that makes sense is if your back is against the wall and you're dying, you have no food, no water, no this, no that, there are still things you need to do as a human being. You need to breathe. You need to eat at some point. You need to use the bathroom. You need to do this. You need to do that. There are certain things that the cell needs to do at all times. And one thing that the cell needs to do at all times is be ready to divide. The cell needs to be ready to divide and also to correct any mutations and changes inside the genetic code. That requires ribose and deoxyribose, correct? Which is going to be produced later on. That means that this pathway can never truly turn off, right? This pathway can never truly turn off. Getting here isn't too hard because we can use some of the things in the middle of the cell in order to just track backwards if we have to. Because the glycolytic intermediates, we kind of always have them around, kind of always have them at our disposal. So if we wanted to make glucose 6-phosphate turn into 6-phosphogluconolactone, we could do that. But do you remember how I said that the NADH and NAD plus ratios sort of dictate how much of this happens at any given time? Right? Do you guys remember how I said that? Where you can turn them on and turn them off and blah, blah, and this and that. And this is also dependent on the amount of insulin we have, which means that it's dependent upon whether or not you had a meal. Wouldn't it be absolutely catastrophic if you needed to have a meal every single time your cell wanted to cure its own cancer? Every single time your cell got a mutation, you need to eat in order for it to fix itself. Wouldn't last one Ramadan, bro. Like, what are you talking about? I'm dead, right? This guy, what's the longest you've gone without eating?
Myself?
While you're deployed?
Deployed 2.5, 3 days almost.
Yeah. Oh, well, what happens then? What are you going to do then?
Grumpy.
That's why, this is why what? The control of ribosynthesis in the pentose phosphate pathway is under the control of the NADPH to NADP plus ratio, not the NADH to NAD plus ratio. You separate the two so that this can happen independent of what's going on over there. This is blocked off in its own world. It's going on whenever it needs to go on. Does that make sense? Do you guys get that? That they have different levels of control. Okay? Rate limiting step for the pentose phosphate pathway is glucose 6-phosphate dehydrogenase. Okay. Are there any other energy saving processes that we have within the body? Is there anything else you guys can think of?
Isn't there like a non-oxidative state where ribose-1-phosphate goes back into?
Yeah, we're not going to talk about that. It's not important. What are you saying? Ketogenesis will happen in low energy states, and we'll talk about that in a little bit. Gluconeogenesis will happen in a low energy state. Take a photo, guys. This is it for insulin. Later. Okay. Huh?
This is way more mind-blowing than the OChem stuff you were talking about.
This is way more interesting.
This is way more like...
I know. I love biochem. I never said I didn't love biochem.
Yeah, but you were like losing it over energy levels for like the...
I just said you're going to suffer.
This is better than amino acids.
Because the thing is that I want you guys to be able to go home and reproduce this by yourself. I'm tired. Okay. Now we do the glucagon-dependent pathways. Insulin was originally released by the beta islet cells of the pancreas in response to having a meal. In that between time, when you had the meal and the energy was fine and the body was fine and we didn't need this and we didn't need to pull back and we didn't need to produce energy and we were okay and everything was going fine, somatostatin sort of kicks in. This is what we're talking about. Somatostatin just puts a wet blanket over everything, says, you know what, we're good. Insulin, glucagon, you're fine. Take a back seat. Everything's going to just go the way it is. After maybe 12, 16 hours, something like that, the glucose levels in the blood, this is the important thing, the glucose levels in the blood begin to drop. We need to maintain a certain level of glucose within the blood in order to feed the brain, in order to keep up the osmolarity, in order to do this, in order to do that. But also, the glucose levels in the blood are also reflective of how much available glucose there is for the cells to use. Because the cells are constantly burning through energy, just doing their natural processes. This is the idea of a BMR, a basal metabolic rate, a basic rate at which your cells consume the fuel that they have to themselves. This is why hyperthyroidism, hypothyroidism, throwback to chapter 5, general biology, we have increases in BMR and decreases in BMR in response to high and low T3 and T4. Yes? Okay. Like, never mind, we'll do that in another video. Okay. So now, when the energy is low, and the thing is, cycling over into this next part of the discussion is really quite simple. You just do everything in reverse. Everything goes backwards. The first place that you get energy from when the glucose level is low and you need to start harvesting energy is the place where you will get the most bang for your buck, right? Where's that going to be? Huh? What'd you say? You said it right. Pyruvate? Not yet. Actually, like, the most bang for your buck, meaning that I'm going to be able to take as many pathways as possible by the destruction of this one molecule. What gives us access to the most of the board? No. The glycogen all the way in the corner. The glycogen breaks down into glucose, and glucose leads to, look, I told you, glucose goes all the way up here, leads to everything in the board. NADH, FADH, GTP, this, that, acetyl-CoA. You can make fats from it. You can go in the citric acid cycle. You make XYZ amount of ATP. You're not starting anywhere in the middle. You're starting all the way over here if you break down the glycogen. So the breakdown of glycogen actually just follows the reverse process. So I'm going to get rid of this. I'm going to say plus glycogenin. And the glycogen can break down back into, this is important. The MCAT wants you to know that it first breaks down into G1P and isomerizes into G6P. They really want you to know that. They really, really, really want you to know that. Because why? Why does that make sense? The majority of the bonds in glycogen are alpha what? 1, 4. And when you break them, you phosphorylate the one end. That's why you make G1P. Does that make sense?
Are you having fun?
I know you're having a great time.
Oh, I'm having a wonderful time.
So the glycogen is, once again, if it's built by 2 enzymes, it's going to be broken by 2 enzymes. Number 1, glycogen phosphorylase. Puts the phosphate on glycogen. Does glycogen phosphorylase use ATP or does it use inorganic phosphates? Huh? How do you know that? It's not a kinase. It would be glycogen kinase if it used ATP, you dummy. Uses PI. And the second one, so that breaks the alpha 1,4 bonds. The second one is known as what? Debranching enzyme. Very easy. Breaks the branches. Huh? Yeah. Debranching enzyme. It's made for dummies like you and me. But then you have freaking succinyl-CoA synthetase, which is named after the reverse process. That it's stupid. It's stupid. It's so dumb. You know the huh? The glycogen phosphorylase will break the alpha 1,4 bonds in the chain. Chomp, chomp, chomp until you get down to the last. Oh, that's such a good question. The glycogen phosphorylase breaks down the glycogen straight chain until you get down to the final couple of monomers. That final couple of monomers has a name. It's like step 1 material. I totally forgot it. I have to look it up for you guys. But the terminus of the chain can't be broken down because imagine this, that you have this, 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 that. And the chain, the branch is right here. The enzyme needs to scoop like this in order to break this. Once you keep going, it's going to get barred off over here. It can't move any further, so you can only chomp up to here. In order to move further, you need to debranch and then keep going. So you will debranch when there's like 2 or 3 units left, and then you'll keep going. So the debranching enzyme breaks the alpha 1,6 connection, whereas the glycogen phosphorylase breaks the alpha 1,4 connection. Understood? Very good. Glycogen phosphorylase is activated by what hormone? Glycogen phosphorylase is activated by what hormone? Glucagon. Very good. This G6P will be able to move back. And in order to reform glucose from glucose 6-phosphate and release it back into the body from any cell that you need, you will take a reverse pathway. I'll do it in a different color, different name, different everything, just so you know it's completely different. Glucose 6-phosphatase. only active in low energy states, low blood glucose, glucagon driven process. And the absolute different color, just so you know it's different. Reversal of that. Even the reformation of glucose in the low energy environment gives you back an ATP to use. Understood?
Is there a specific name for that pathway, or is it just like no way?
It's called glycogenolysis. The breaking of glycogen. But you're talking about this pathway?
Yeah.
This is just reformation of glucose. All pathways that will reform glucose end with that step.
So with the glycogen synthase and the branching enzyme for the glycogenesis, is that occurring from glucose 1-phosphate to UDP glucose?
Yeah.
Okay.
Yeah.
Glucose 6-phosphate to glucose 1-phosphate.
So it's the glucose 6-phosphate turns into glucose 1-phosphate first. Then the glucose 1-phosphate turns into UDP glucose and into glycogen. Gets added to the glycogen monomer.
The synthase and the branching.
Yeah. Exactly. Next, in order to maintain the glucose levels within the body, we need to also be able to harvest some of the glucose intermediates that may be going on in the process of producing energy at the current moment for the cell, so that we can send glucose back off into the body whenever it's needed. This is a pathway that kicks in much later in the process. This will kick in maybe 24 to 48 hours after not eating, right? You get a blistering headache when this kicks in. Like crazy, crazy, crazy headache. The gluconeogenic pathway is dependent upon the fact that the cells are running out of energy and running out fast, and that the brain needs glucose. The brain only has two fuel sources. What? Glucose and ketone bodies. Right? In massive starvation, it can use ketone bodies. Gluconeogenesis is the production of new glucose. Happens within the liver and slight tiny bit in the kidneys. Just a little bit. Gluconeogenic pathways need the ability to overcome the irreversible steps of glycolysis, which are three: pyruvate kinase, PFK1, and hexokinase. I already showed you how to reverse hexokinase. Let's go over how to reverse the other ones, and the rest of it is a downhill battle. To reverse pyruvate kinase, we actually have a two-step process. We first take the pyruvate and we turn it into what? Oxaloacetate, OAA, which is the same thing that we saw right here inside the citric acid cycle, right? The same thing that we saw right there. We will take CO2. Hold on. Colors. This enzyme is called pyruvate what? Carboxylase. Look at the difference between pyruvate and OAA. It's just one carboxyl group. We take a CO2 group, put it on here, sorry. And if you want to know, biotin is a cofactor here. Biotin is vitamin B what? B what? Someone tell me. Is it 6 or is it 7? B7? Who says B6? Yeah. B6 is what? Peroxidine, or whatever it's called. B7 is biotin. B1 is thiamine. B2 is riboflavin, so NAD and FAD, right? B3, niacin, right? Sorry, niacin is NAD, my bad. Thiamine is using thiamine pyrophosphate. So B1, B2, B3. Is there any B4? There's no B4 because it sounds too much like before. B5, pantothenic acid, right? B6, pyridoxine phosphate. B7 is biotin. Is there a B8? Is there a B9? Folate, very important for pregnant women. Is there a B10? Is there an 11? And is there a 12? Cyanocobalamin, very good. Important for neurologic development and blood cell production. Do you need to know that for the MCAT? No, but isn't it cool to just sort of know these things? In the same way that it was very difficult to throw the acetyl-CoA onto the oxaloacetate, it is incredibly difficult to put a CO2 group on something that is already negative and produce another negative charge on top of it. And for that reason, we need the input of what? ATP. Ya Allah, I'm so tired. OAA will turn into PEP through one of the coolest enzyme names ever. PEPCA. Phosphoenol pyruvate carboxykinase. PEP carboxykinase. Kinase means it uses GTP. Very good. GTP, GDP, and this one doesn't go to waste. It gets attached to the molecule. And the CO2 leaves.
Is there a specific reason as to why sometimes it's like ATP versus GTP?
I'm sure that there's a biochemical reason for the nuances between which nucleotides to use versus which ones not to. It's just beyond my capacity, and I haven't looked into it. I have never been afraid to tell you that I don't know. But I think you should do it for us. Why don't you go home and look it up and give me an answer by Sunday? Someone set a reminder. Actually, I'll give you a week. Someone set a reminder for next Thursday at 7 p.m. that Zaid needs to get in front of the class and explain to us why there's a difference between the ATP and the GTP inside of these processes.
I got you.
And he has to do it on the board, on camera.
Putting it in my calendar.
Thanks, man.
You're welcome. Build some confidence. I'm doing you a favor if you think about it. PFK1 is the next step that we have to overcome. Very simple. Fructose, 1,6, bisphosphatase. What happened? Zaid sacrifice?
You know, I put sacrifice inside sacrifice, sounded more fun.
Is this like Corbani but like earlier?
You know, like that one thing Julian means?
You know Zaid.
Humiliation ritual? You know the one board?
Fructose 1,6 bisphosphatase reverses the irreversible process of PFK1, also acts as the rate-limiting step of gluconeogenesis, and prepares you to go straight down the hill in order to reform glucose 6-phosphate and give you the glucose to put back into the body. Understood? You guys good? Kind of like it up here. How's my audio? How's my video? The potent activator of fructose 1,6 bisphosphatase is actually the lack of fructose 2,6 bisphosphatase. This makes sense. Why? We're talking about glucagon pathways, right? Glucagon strips the PFK2, activates the fructose 2,6, activates fructose 2,6 bisphosphatase, also known as FBPase2, right? Fructose bisphosphatase 2. You can also write this as fructose bisphosphatase 1, right? But since I wrote that convention, I'll write that convention here as well, just for the sake of consistency. No, we're gonna do it next week.
On Thursday?
Yeah.
My lab starts next week.
I'll send you the video, don't worry. I'll specifically send you the video.
Thanks.
I might not upload it on YouTube just for his sanity, But I might blast him on the Discord. That's what I might do. Join the Discord channel, guys. Links in the description if you want to see Zaid get cooked.
The Discord channel makes me feel like a creep every
The Discord channel is scary.
It's weird, man.
Can I get
The Discord channel is weird. Were you there? Were you in the Discord channel when all that stuff happened with that guy?
Yeah, I saw that.
It's
The
crazy.
one, like,
Yeah, the one. Yeah.
I saw that like
Can you-
right when I saw notification.
Can you say the at on YouTube like right now so he knows?
I don't remember, dude. I banned him the second I saw that. It was crazy. Yeah, it was wild. Yeah, you can talk about the story later. Okay, so doesn't it make sense that the activation of this domain by glucagon makes the fructose 2,6-bisphosphate disappear? By stalling the PFK1, we activate the reverse pathway, correct? So the glucagon is really what's doing the work here. What else happens? My teacher told us today that he hid something from us. When we were learning verb conjugations, he told us to write something a certain way, but it actually wasn't the proper way of writing it. If you know, does anyone here know Arabic? How to write Arabic? Or like the rules? So like Arabic, there's a specific letter in Arabic that has a lot of rules to writing it. It's the hamza. The hamza can be written like that, or it can be written like this, or it can be written like this, or like that, or like that. There's all these different ways of writing the hamza.
Your Arabic is better than your English.
And depending on what it looks like in the word, it's going to be one of these 5 choices, right? And he told us to write it like this, when in reality you're supposed to write it like this, but we just weren't ready for this discussion yet. So he held off. I have been holding off on a discussion from you. Now we're going to have that discussion. This pathway is actually stopping another pathway. And I've spoken about this before. That in order to take the fatty acids, and in order to get acetyl-CoA back from them, we actually need to be able to do some very interesting chemistry. I want to get this right, because this you actually need to know about. This is beta oxidation, yes. Let me find a good image here. A long-chain fatty acid where does fatty acid oxidation take place? Someone look it up. Someone look it up. This is a fact I always get wrong. Someone look it up.
It primarily happens in the mitochondrial matrix, but also takes place in
It primarily happens inside of the mitochondrial matrix. And these fats and triglycerides exist within the cell. There must be a transporter. One of those transporters is known as the carnitine transporter. There's a carnitine transporter that brings in these fats. That transporter, I don't think it's worth the squeeze. I never fully understood it myself. I'll openly say that. But one of these transporters is known as carnitine palmitoyl transferase 1, CPT1. And this brings the fatty acid into the mitochondria. And I'm going to draw the fatty acid like this. All right, you guys really got to lock in for this one. Okay? We take this fatty acid. Really going to focus to get this right. Because this is actually something you need to know, and they want you to know this by heart. I don't know why this and not the synthesis, but here we are. That the fatty acid will be turned into fatty acyl-CoA. SCOA. So you have an input of S-CoA, blah, blah, whatever it is. You will then have the action of FAD turning into FADH2. which will make a double bond right there. You will then add water. Just like the citric acid cycle, when we added water to the double bond, we get a OH. SCOA, OH. We will then use NAD. And we will then add CoA, turn to acetyl-CoA, and this will go back and act in that first step of the reaction. And you have now shortened this fatty acid by 2, releasing an acetyl-CoA molecule. Does that make sense? CoASH is just coenzyme A with its hydrogen attached. Got it? Good. Very pretty benzene ring. The acetyl-CoA is then allowed to go into the Krebs cycle. Fatty acid oxidation gives us acetyl-CoA to make energy for the cell. Gluconeogenesis gives us glucose to send out to the body and the brain. Glycogenolysis gives us both. It can go forward or it can go back depending on the energy status of the cell. Remember that the activation or deactivation of glucose, and whichever way it goes, is dictated by the forward or backward reaction of PFK1 and FBPase1, which is dictated by the energy status of the cell. You should be able to understand that when I say that. Do I need that run again? Okay. The forward or backward process of PFK1 or FBPase1 or F16BPase is dictated by the energy status of the cell. If you did glycogenolysis and there was low energy in the cell, it is more than likely that the glucose phosphate will move forward and go towards acetyl-CoA. Whereas if the energy status of the cell was high and the body needed the glucose, it would go backwards and get transported out.
How easily can the brain use ketone bodies?
Very easily. Where do ketone bodies come from? Let's say that ketone bodies are very simple. Let's say that you're very hungry, starving. Your body's going to start burning through fat slowly in the beginning in order to just like feed the citric acid cycle. Eventually, when you completely run out of sugars, it's going to start burning fats left, right, and center, right? It's going to go, fire on all cylinder burning fats, right? This is really like, it doesn't really happen like during a Ramadan fast. Like people are like, oh, Ramadan helps you lose fat. Yes, it does, because we do it for 30 days straight. And your sugar levels, like what happens to your sugar levels every day is that they deplete and deplete and deplete and deplete and deplete. So instead of taking 16 hours to burn through your sugar stores, it takes like 8 or 9 by the end of the month, right? So, and obviously, like if you concert your meals the way that you're actually supposed to, right, it gets even lower and then you burn fats quicker.
Is it because your insulin sensitivity goes down?
Your insulin sensitivity goes up throughout the month.
Really?
Yeah, your insulin sensitivity goes up because of chronic hypoglycemia, relative hypoglycemia. Yes?
I'm lost at the one that you just did after the NA plus and the NADH plus H arrow. Just like the last little bit.
This, do you see how right here we have a coenzyme A molecule hanging on the end of this? When you add the coenzyme, when you add CoA, it's going to attack here and kick off this acetyl-CoA molecule.
Okay.
Kick off these last two and attach a CoA to the end. Do you see how this is just that and this is just that? Look. You get me up to here, right?
Mm-hmm. Yeah.
Add CoA and cut.
Okay.
That's it. That's all we did. We cut the bond and we added the CoA to the end. What's not making sense?
I just don't get why.
To make acetyl-CoA.
But like, why is the byproduct like that?
Why is it like? Because it's the fatty acid minus the 2 carbons from the acetyl-CoA.
Oh, okay.
Yeah. This is, let's say that this was it, right? This is a 1, 2, 3, 4, 5, 6 carbon fatty acid. After we cut the end, remove the acetyl-CoA, now we have 4. We removed 2. We had 6, we removed 2, we had 4. Right? What was the secret I wasn't telling you guys? The biggest thing to know about these pathways. And the true mark of someone who understands biochemistry is the understanding that the activation of acetyl-CoA carboxylase by insulin inactivates or deactivates the breakdown pathway. That malonyl-CoA is a potent inhibitor of carnitine palmitoyltransferase 1. Potent inhibitor. Meaning that even when the cells have a lot of fats in them and we are fed, the reason you don't burn those fats in order to make even more energy for the cell is because insulin activates acetyl-CoA to turn acetyl-CoA into malonyl-CoA, which turns off the breakdown pathway. The natural state of the body is one of fat burning. When you eat a meal, the malonyl-CoA made from the interaction of acetyl-CoA with the activation of insulin with acetyl-CoA carboxylase produces a byproduct that shuts down that process. Fatty acid synthesis is actually not the default. The default is fatty acid breakdown, which is why what? It's so easy to put on weight. All you have to do is eat. And if you eat in excess, you turn off the fat burning process and you build fats. It's very easy, very simple. You turn off the default of the body to burn energy and you stop that. Does everyone see that? Do you see that this whole thing, everything we just drew here, is invalidated, irrefutably just punished, completely snuffed out by the presence of insulin? Does that make sense? Ketone bodies come from the fact that you, and we went on a little bit of a tangent, you burn and burn and burn and burn and burn fats. And you get a buildup of acetyl-CoA. Those two high energy molecules can smash into one another and they'll produce ketone bodies. That's it. Those two high energy molecules collide, make ketone bodies, you send them out to the brain. And it uses them to reform acetyl-CoA and use it in its own citric acid cycle. Does that make sense? Very simple. Very easy. However, so there's a little bit of like weird byproducts there, blah, blah, blah. A lot of ketogenesis can give you acidosis.
Does it not take a lot of energy to smash together?
Not really, because they're both high energy. Remember, carboxylic acid derivatives, very high as thioester. They can just naturally smash together. The most common ketone that you'll hear of, especially in medicine, is beta-hydroxybutyrate. Beta-hydroxybutyrate. And acetoacetate. Which makes sense because it's acetyl-CoA and acetyl-CoA. Acetoacetate is just smashing them together. That's ketones. I wanted to do shuttles. I don't think it's high yield enough. Gluconeogenesis, glycogenolysis, ketone bodies, fatty acid breakdown, fatty acid synthesis, ETC, citric acid cycle, glycolysis, PFK2, pentose phosphate pathway, DNA synthesis, glycogenolysis, glycogenesis, insulin. And you know that the breakdown of fats from here, before we make the fats, will also make glycerol. Glycerol will plug back into the pathway. Go backwards if you need glucose. Go forwards if you need acetyl-CoA. You guys get that? You You'll oxidize and phosphorylate. Glycerol dehydrogenase will give you glyceraldehyde. Glyceraldehyde phosphate will be produced by the phosphorylation. Fructose metabolism, very quick note on that, is able to circumvent PFK1. Because what you can do is you can phosphorylate the 6th position of fructose and then just chop it, and that'll give you GAP. That'll give you glyceraldehyde phosphate, right? And dihydroxyacetone. That glyceraldehyde phosphate can just move forward and bypass PFK1. What have you effectively cut out of the picture? The slow step of glycolysis, which is why powerlifters, when you see that they need a big spike of energy, like whatever it is, they'll chew on like gummy bears and drink apple juice because it's chock full of fructose. Very, very rapid energy sequestration that bypasses the slow step of glycolysis. Urea cycle, we can do when we do the rest of biochem. It doesn't really fit on the board here. That's the thing. It has a little bit of an overlap with the citric acid cycle, but I think this is like, I think this is enough of like crap on the board. Do you guys want to name everything?
I think before that, how does amino acid?
It plugs in somewhere here.
Okay.
What? What do you think? Okay, let's do it. Let's name everything. You know what? Why don't you name everything? All right, what do we start with right here? What is this? We have glucose. You know what? I'm not going to write it. There's already so much clutter on the board. This is glucose. This is glucose 6 phosphate. Then fructose 6 phosphate. Fructose 1,6 bisphosphate. DHAP and GAP. Then glyceraldehyde 3 phosphate in the form of GAP. Then we have glyceraldehyde. We have 1,3-BPG. 1,3-BPG. Oh man, 1,3-BPG. 1,3-BPG in red blood cells can mutate into something known as 2,3-BPG. 2,3-BPG. Oh wow, we're gonna be here for another 15 minutes. Oh, that's so exciting, man.
That's great. I just told the janitor 20 more minutes. I had to use Google Translate.
Get the hell out of my... All right, no, this is gonna be quick, I promise. The natural state of hemoglobin is to be in a very high affinity. No, you don't need to write this. It's fine. It's fine. The natural state of hemoglobin is to be in a very high affinity state for oxygen with an unrelenting desire to hold on to it, right? That is indicated by something like this. Huh? Yeah. There is still, huh? Yes. I'm glad you know that. Good. The rightward shift and loss of that affinity. Guys, shut up. The rightward shift and loss of affinity for glucose is implicated by the existence of 2,3-BPG on the erythrocytes, which binds the hemoglobin and changes its affinity for glucose. So we have a rightward shift in the curve, which is indicated like this. Very slight differences. However, these slight differences make let me make it a little more dramatic, actually, just for your understanding. That's better. This purple curve is indicative of adult hemoglobin, whereas the black curve is indicative of the action of fetal hemoglobin. Where fetal hemoglobin, the only difference is that it actually doesn't have the ability to bind 2,3-BPG. And because of that inability to bind 2,3-BPG, at a certain partial pressure of oxygen, let's say over here is 50, over here is 80, over here is 100, we will have different concentrations. At 100, they are both at 100% saturation, meaning that 100% of the sites on all hemoglobin molecules within that specific sample are booked, right? And we may go down to 80 and 65 and 40 and 20 and 0. This is percent saturation, meaning of a total class of sites. Of a billion sites, what percent are occupied? I'm not talking about one cell. I'm not talking about one specific hemoglobin molecule, right? And over here, we have the partial pressure of oxygen within the environment. Not in a cell, not on the red blood cell, not in the body in general, of the environment within which the red blood cell carrying the hemoglobin exists at that specific time. That's what we're talking about. And we go to 30, and we go to 20, and we go to 10, and we go to 0. You will see that adults normally do walk around quite a bit more than idiots who can't even walk. And we have higher metabolic demands. And because of those higher metabolic demands, this whole thing is happening a lot more. Oh my God, there's so much on the board. This is happening a lot more. Like from here, it looks like scary. This is happening a lot more. So you see that the disappearance of oxygen is actually a little bit faster, right? We have higher energy demands. We have this, we have that, right? And we have more demands for like shivering thermogenesis. You know, like babies can do that whole non-shivering thermogenesis thing with their brown fat, things like that. Babies are interesting, right? They also hold their breath underwater naturally, which is like weird. And they can support their entire body weight with one hand, if you didn't know that. So the oxygen disappears faster from the adult, which means that the environmental oxygen concentration is on average lower. On average lower, correct? But we're going to actually flip that statement in just a little bit. Stick with me. So when we're active, it's possible that all the way down here, let's say in my legs right now, I've been standing for a long time, the average partial pressure of oxygen is roughly around 50, right? 50 millimeters of mercury. This is in millimeters of mercury, correct? At that point, how much... Hi everyone, my phone died. We just went over 2,3-BPG and the hemoglobin curve, and we just named all of these molecules, but we've done that already. There's nothing else that's on the board. Thank you guys for watching. Check out the description. I'll see you soon. Happy studying.